more log exponential kind of stuff.
Okay, I just did a session on logs and exponentials for a full hour, so I should be up to speed perfectly.
Fantastic. Ooh. All right, so to start, sorry, hold on, let me get to that page really quick.
Of course, now that I remember, you give me interesting log equations that I don't get elsewhere. So maybe I shouldn't speak too soon.
Well, you've been able to help, so I'm confident this will be good.
Okay.
Okay, so the directions are just solve the equation for x,
Okay.
and it's log base x of 1/8 equals 3.
Okay. Whenever you have a log equation, solve it by converting it to an exponential equation.
Okay,
What's the
so
exponential representation of this?
x to the third equals 1/8.
Uh-huh. Now, can you figure out what x has to be?
It has to be a fraction, correct?
Well, we can solve it algebraically. In other words, now we have an algebraic expression. So I want to take the cube root of both sides.
Right.
Cube root of the left side is x. What's the cube root of 1/8? What fraction multiplied by itself 3 times equals 1/8?
1/2.
Yeah, positive, not plus or minus.
Right, because the minus is extraneous, or
No,
because
no, it's because only 1/2 times 1/2 times 1/2 equals 1/8. If I had negative 1/2, it would equal negative 1/8. So taking cube roots is not the same as taking square roots. In other words,
oh,
if I took the square root of 4, it's plus or minus 2. But if I take the cube root of 8, it's plus 2 only. And if I take the cube root of minus 8, it's minus 2 only.
and is that because the cube is an odd root?
Yes.
Okay.
In other words, odd roots, negative numbers are fine. And you
Right.
produce a negative answer. You
Oh,
cannot take the square root of a negative number.
right.
But you can take the cube root of a negative number and you get just negative. If you take the cube root of a positive number, you get just positive. You don't have the plus or minus like you have when you take square roots of numbers.
Okay. All right. Um, log base 2 of 2x plus 1 equals 3.
Okay, what's the next thing I want to write?
Make it 2 to the third, 2 cubed equals 2x plus 1.
Now you have a simple algebraic equation.
Right. Oh, I tried taking the cube root of this one.
Yeah, you don't need to. That actually makes it harder to solve for x. In other words, once you get to the algebraic expression of that log expression, then you're trying to isolate x only. So you don't want to be taking the cube root of the right side. It just makes x more complicated to get at.
Right. Okay. Um, the next one is log base 6 of 36 equals 5x plus 3.
Now I could say 6 to the 5x plus 3 power equals 36.
Right.
But that one's going to be hard to solve. I'm not going to know how to solve that. Let's look at that first. What is the log base 6 of 36 equal to?
Log base, like the whole log itself?
Yeah, in other words, this is a log we can evaluate without a calculator.
Right, it's just 6, isn't it?
No. If
Sorry,
we make up a variable,
2. I'm sorry, I meant 2.
2, exactly. In other words, making up the variable helps a little bit when you're going to try to evaluate that log expression. Because now I know that 6 to the x has to be 36, x has to be 2, which means that's 2.
Right.
Okay, so well, if I substitute 2 for this, then I get a simple algebraic equation. 5x
Okay.
equals minus 1, x equals minus 1/5.
Okay. All right.
In other words, some of these log expressions you can evaluate without a calculator. That's one of them.
Right.
And that's
Okay.
what you want to do, because if you try putting that in an exponential, it'll be harder to solve.
Okay. E to the power of 2x plus 5 equals 8.
Okay? Here we have an exponential equation. Don't have algebra to solve this. But the way I solve exponential equations is by taking the natural log of both sides. I can still do whatever I want to one side as long as I do it to the other side.
Right.
Now, what is the left side? In other words, I can look at this of one of two ways. I can bring the 2x plus 5 down in front like this. What's the natural log of e equal to?
1.
And now I have an algebra equation. So 2x equals natural log of 8 minus 5, which makes x natural log of 8 minus 5 divided by 2.
Okay.
Okay? So whenever you have an exponential expression or equation, you can convert it to an algebraic one by taking the natural log of both sides. And I would use natural log regardless of whether that was e or not.
Okay.
In other words, let's say that was base 6. My expression or my equation was this. I've got 6 to the 2x plus 5 power equals 8. Okay?
Okay.
I still have to take the log of both sides, and some people might be tempted to take the log base 6 of both sides, but it's not really, it doesn't save you any time or steps. Just always take the natural log of both sides. And now I've got 2x plus 5 times natural log of 6 equals natural log of 8. Now I got 2x plus 5 equals natural log of 8 divided by natural log of 6. Now I got x is going to be that quantity minus 5 all divided by 2.
Okay.
So even if your numbers are not e, you still use natural log. In other words, that ratio right there is, believe it or not, the same as common log of 8 divided by common log of 6. Also the same as log base 17 of 8 divided by log base 17 of 6. So these ratios are all the same regardless of what base is used.
Okay.
In other words, if you go into your calculator and look up natural log of 8 divided by natural log of 6, it's going to give you the same number as if you did common log of 8 divided by common log of 6.
Okay.
Which is an interesting observation. those ratios are always the same, which means I can use common log of both sides or natural log of both sides. The only difference, had I taken the common log of both sides for this problem, well, then I would have common log of 8 over common log of 6. Same number as natural log.
Okay.
So I always use natural log, and it's because the natural log is the language of calculus, not common log.
Right. You mentioned that.
Pretty much everything goes to natural log. And so
Okay.
the sooner you get used to it, probably the better.
All right. Okay. The next one, it says determine the domain and range
Okay?
and find the vertical asymptote of each function. Verify the results using a graphing utility.
Okay?
So it's f of f of x equals negative ln, or natural log, sorry, of x minus 1.
All right. Determining the domain. What's the domain of this?
1 to infinity.
0 to infinity.
It is.
Huh?
Even with the transformation.
Well, no, hold on. No. I just was starting with a more simple one.
Oh, okay.
Okay? In other words, when you have a natural log function, the argument has to be greater than 0. It cannot even be equal to 0.
Right.
You cannot
That's
take
different.
the log of 0. You can take the log of 0.00001, but you cannot take the log of 0. So that's the domain for that function. So basically, the way we figure out domain for a more complicated function is we take the argument and we say it has to be greater than or equal to 0. X minus 1 has to be greater than 0. Not greater than or equal to, sorry, greater than.
Okay.
Whatever is in the argument, you can make this statement, which means x has to be greater than 1. That's your domain. If you want to put it in interval notation, it's 1 to infinity.
Okay.
The consequence of that negative sign is none for the domain.
Right.
And if you graph a natural log function, it looks like that. So you can see that the domain is 0 to infinity. The range is negative infinity to positive infinity.
Okay.
Okay? Now, let's talk about vertical asymptotes. This is a translation to the right of 1 unit, right?
Correct.
Well, if my black line over here is y equals natural log of x, what's the vertical asymptote on that?
X equals 0.
So move that 1 unit to the right. That's the new vertical asymptote.
Okay.
And we're going to reflect it because of the negative sign in front. So if I drew this curve here, that red curve is going to be y equal negative natural log of x. And then I'm going to take that red curve and move it 1 to the right so that it looks like that. And that's going to have an asymptote of x equal 1.
Okay.
In other words, whenever you're doing a horizontal shift, you take all your vertical asymptotes and shift them by that amount.
Okay.
The vertical reflection does not affect the vertical asymptote. It has nothing to do with it. In other words,
Right.
the vertical asymptote's the same for this function as it is that function. Well,
Oh,
not the same, 1 over. But it's
right.
the same as y equal minus natural log of x. These two have the same vertical asymptote. The vertical reflection does not affect the vertical asymptote.
Okay. All right. The next one is just solving for x again.
Okay.
It's log base 5 of x squared plus x plus 4 all equal to 2.
Again, whenever you have a log equation, convert it to exponential. You'll see that it's very solvable then.
Right.
So what's the exponential?
5 squared equals x squared plus x plus 4.
Now that's just a simple quadratic. That becomes 25. Move it to the right. We got 0 equals x squared plus x minus 21. And now you're going to have to use the quadratic formula on that to solve it.
Okay.
But that's okay. In other words, I can't factor that easily.
Right.
I can't factor it at all. I've got to use the quadratic formula to solve for x.
Could you complete the square too?
You could, although, yeah, if I'm going to complete the square, I'm going to put that 21 back on the other side. In other words, if I'm completing the square, I can do it real quick. I'm going to leave the 21 over there. Now I'm going to complete the square by adding 1/4 to both sides. Then the left side, you saw why I added 1/4 to the left?
Yes.
Now I can write that as x plus 1/2 quantity squared equals 21 1/4. Now I'm going to take the square root of both sides. Let's see, that's 85/4 plus or minus. And now x equals minus 1/2 plus or minus square root of 85 over 2. And
Okay.
I don't think I can simplify square root of 85. It's not divisible by any of my perfect square numbers.
Right.
So that's what you would have gotten had you plugged it into the quadratic formula also.
Okay.
Okay, and it's almost easier. In other words, once I get to this step here, well, the quadratic formula is x equals minus b plus or minus the square root of 1 minus a minus 84 all over 2. So the quadratic formula actually is a little quicker. 1/2 plus or minus the square root of 85 over 2.
Gotcha.
It took me less time to use the quadratic formula than it did to complete the square.
Okay.
Both produced the same answer. In fact, the quadratic formula was derived from completing the square.
Okay.
If I tell you that I have a quadratic that's like this in standard format, and I want to solve this quadratic by completing the square, I move the c over, I factor out the a, I do everything I would do, and you end up with the quadratic formula.
Right.
It's not a bad practice to go through every now and then. I've only done it once, but it works. It's not an easy thing to complete the square of, but it does give you the quadratic formula.
Okay. Interesting. Okay. This one just saw more solving.
Okay.
So 1/2 log base 3 of x equals 2 log base 3 of 2.
Okay. Now, let me think for a second here.
What I did was I put...
Let's condense these. Take that coefficient that's in front of both and make it an exponent.
Okay.
So that gives you this. Right?
Mm-hmm.
Now, if I have the log base 3 of one thing equals the log base 3 of another thing, then I can equate the two things. That means
Right.
x to the 1/2 has to equal 2 squared. Now square both sides, you get x equals 16.
Okay.
And one further word of caution. Always take your answer and make sure you do not violate any domains.
Right.
Well, I can take the log base 3 of 16. Had I gotten an answer that was plus or minus 16, I would have to throw out the minus 16 because
Right.
you cannot take the log of a negative number. So typically, log equations, whenever you produce two answers, check both of them. Almost invariably, one of them will violate the domain and needs to be thrown out. In other words, you end up with a lot of extraneous solutions when you're solving log equations.
Is it impossible
Not
to
this
get...
one, but others. Go ahead.
Is it impossible to get more than one answer for x in a logarithm problem like this?
No,
Not necessarily
at all.
like this.
Here, let me give you an example. Now, if I put these two together, which is the way to solve this, make sure you understand what I'm doing here.
Mm-hmm.
Okay.
Right.
Now, that's common log, so it's 10 to the 1 power equals x squared plus x, which means x squared plus x minus 10 is equal to 0. That's going to produce two solutions, right?
Right.
I
Okay.
can't factor it, but I can guarantee you that if I plug that into the quadratic formula, I get a plus and a minus solution. The minus solution is no good because it's going to violate that domain right there.
Okay.
The plus solution is fine. It doesn't violate either domain.
Right.
Here's the key. You cannot check your domain violations from that step there. Notice that a negative number would not violate this domain. I would end up with a negative x times a negative number. The argument's going to be positive. So an x value of, say, minus 2 does not violate that domain, but it does violate the domain of the original equation. So you have to be very careful. You cannot check your domains with any part of the equation except the original equation.
Okay.
These two may look the same, but they're not entirely the same.
Right.
In other words, I can have negative numbers for x in this expression. I cannot have negative numbers for x up there. So just because I use my rules of logs to compress this, it does change the domain considerations. And you have to be careful about that. Always go to the original.
Okay. So another quick question. For the graph of a log, what does the solution look like? Because it's not the x-intercept. So how could you precisely identify, without using any calculator tools, just looking at a graph, how could you determine the solution, or can you?
So this function here is y equals natural log of x. So when you say determine a solution, not sure exactly what you mean.
Is there a way to simply look at a graph and determine what x is?
No, because x is variable. In other words, x is the independent variable.
Okay.
X can be anywhere from 0 to infinity in my graph here. Depending on what x is, y is something. Well, if x happens to be the number e, then y is 1. In other words, that point right there is e comma 1. When x is e, y is 1. Natural log of e is 1.
Okay.
Okay? So when you have a graph, there's really no solution. There's x-intercept. You could figure out what the x-intercept is.
Right.
And the x-intercept is going to be 1 comma 0. In other words, when x is 1, y is 0. The natural log of 1, the log of 1 is 0 regardless of what the base is. The natural log of 1 is 0. The common log of 1 is 0. The log base 18 of 1 is 0. Why? Because all of these bases to the 0 power equals 1. Any number to the 0th power is 1. So when you have a graph, it doesn't really make sense to say, well, what's the solution for x or y? Because it depends. In other words, you've got an independent variable, which is x, and you've got a dependent variable, which is y. So given a certain x, you can figure out what y is. But there's no solution that y equals something or x equals something, unless you're talking about the zeros of the function. If you're looking at that function and you say, what are the zeros? Well, that means where does it cross the x-axis? Now I can figure that out. It crosses the x-axis at 1 comma 0.
Okay.
Your question leads me to believe that we should do one where we have to do what you thought you had to do there.
Okay. With what sort of directions?
Well,
Yeah.
you asked me, can you tell what x is from the graph? Not if it's a single function. If you have two functions, then it's the intersection of the two. In other words, if I have a natural log function combined with a straight line function, well, now I got two x solutions, that and that. So I can figure out what x is if I have two different functions graphed, but if I only have one function graphed, it doesn't really make sense to ask what x is or what y is. They're both dependent on one another. You can let x equal whatever the domain allows for, and then y is going to be equal to some number.
So if I have problems with the directions, solve each equation, verify your solution using a graphing utility.
Ah, okay. Now let's see if I can back up to the one that had that. I still have difficulty with this program, figuring out how to back up pages. I thought I knew how, but...
Is this the OneNote application?
Yeah, this is a Windows 10 notebook. Let's see, if I put it under Draw, I can back up one step at a time, but I don't know how to get back to a previous page.
I can just give you another problem.
Okay, let's do that. That's
log of x plus log of x plus 15 all equal to 2.
This is going to be a problem that's going to give us two solutions, and one of them will violate the domain.
Okay.
The first step here is to combine it into a single log expression. Because once we get it into a single log expression, then I can convert it to exponentials and solve it. So what's the single log expression going to be here?
Log of x times the quantity of x plus 15.
Which is x squared plus 15x, okay.
All equal to 2.
Okay, now what? Put that into exponential format.
10 squared equals x squared plus 15x.
So x squared plus 15x minus 100 equals 0, correct?
Correct.
Now this one I'm hoping would factor. Would they be so nice? What factors of 100 subtract to 15? I don't think we're going to find any. Oh yeah, 20 and 5.
Yeah.
Which means x is equal to minus 20 or x is equal to 5. Well, x cannot be equal to minus 20. It violates that domain right there, and it violates that domain.
Right.
Notice that if I were to check the domain on that, it does not violate them.
Right.
X squared minus 20 squared is 400, minus 300 is still 100. So your argument remains positive even with the minus 20. So this is the perfect problem where you have to go back to the original problem to eliminate one of your solutions.
Okay. So
now in terms of graphing this, what do they want you to do in terms of the graph?
It just says verify your solution using a graphing utility.
Okay. If I put that, what kind of graphing calculator do you have?
A TI Nspire.
Okay. Are you familiar with Wolfram Alpha?
No.
A beautiful little program. Here, let me pull it up. I'll show it to you. I don't have a TI Nspire clone on my computer. I used to have a TI-84 clone that I could bring up.
I have a TI-84 if you want me to get that.
No, I'll do it here and we'll see what the solution is.
Okay.
The problem was log of x plus log of x plus 1
x plus 15
plus 15
equals 2.
Equals 2. The beauty of Wolfram Alpha is that it shows you what you put in. Okay? And notice what it graphs. Two different functions. It graphs the log functions and then it graphs 2, y equal 2. And wherever they cross, that's the solution.
Okay.
Our solution was 5, right?
Yeah.
Well, that doesn't look like 5.
No.
Log of x what did I do here? Did I write it correctly? The log of x plus the log of x plus 15 equals 2. Multiply those two arguments together to get x squared plus 15x. Exponentiate it, you get 10 squared equals that. So that's correct. That's correct. X equal 5 is the solution. How come Wolfram alpha doesn't show that? Oh, no. Well, first of all, that solution there isn't the solution. It's the x value of that.
Okay.
Okay, in other words, if I want the x solution, it's whatever that number is.
4.77. Yeah.
But even that's not right. We came up with 5 and minus 20. Well, I'm a little puzzled as to why it doesn't come up with x equal 5 at that point. Good explanation for that. I am certain that we did it properly. My only mistake was pulling up Wolfram alpha to figure it out. I cannot explain that little discrepancy there. The way we did it was the proper way here.
Okay. Okay.
And we can prove it.
Right.
In other words, if I want to prove that 5 is the solution, then all I have to do is prove that the log of 5 plus the log of 20 equals 2. Well, if you go into your Inspire and type common log of 5 and add it to common log of 20, you'll get a number very close to 2.
It's exactly 2.
Yeah. I was thinking maybe there'd be a little round off error, so you might get something like 1.9999999. So 5 is definitely the solution. Yeah, I don't know what I did wrong with Wolfram alpha, that it didn't show 5 as the solution. That's very odd. What else? Incidentally, the way to figure out the solution, if you have something like this, is let this be y sub 1, let that be y sub 2, if you're on a TI-84, and wherever they intersect is the solution.
Okay.
In other words, the log of x would look something like that. The line y equal 2 would look something like that. Well, there's your solution.
Okay.
In our case, that would come at x equal 5. When I had the log of x squared plus 15x equals 2. It would produce a picture that looks like this. And wherever they cross, that's your solution.
Okay.
Now, logs are a little bit like square roots. If you can actually take the log of a negative number, but you get an imaginary answer. In other words, if I want to take the log of minus 7, I can do it, but only by incorporating complex numbers. And I've never seen that done in high school.
Okay.
That's advanced college, where you start using complex numbers as part of logs. I never see that done in high school. Whereas in high school, everybody knows what the square root of -4 is. It's 2i.
Right.
Well, the same I comes up when you violate the domain, just like I violated the domain by taking the square root of a negative number. That's how I get I. Well, when you violate the domain of logs, you get I also.
Okay.
And that may have been what was going on with Wolfram Alpha, because Wolfram Alpha gives you the positive, it gives you the real and the imaginary solutions.
Okay.
Still don't
Gotcha.
know why. And look at this solution they came up with. Square root
Yeah.
225 plus 4e squared. Huh. Well, notice what that is.
The quadratic formula.
I was thinking it's 15 plus 2e, but it isn't. That's not what the square root of that is. It's just a very interesting solution they came up with. Completely different.
It's equal to 0.477409.
This thing here?
Yeah.
Which is what the graph shows.
Yeah.
Assuming, here's the problem. Assuming log is natural log. They interpreted this as natural log instead of common log. Use the base 10 log instead. Well, if I click on that, now it's going to give me a proper chart, and my x value comes at 5 right there.
Okay.
Okay? So
Gotcha.
it wasn't Wolfram Alpha that was screwing up. I was putting the wrong log in there. When in Wolfram Alpha, if you type log, it assumes natural log. That's how natural logs are, is that Wolfram Alpha assumes natural log when you type log.
Okay.
Who would have thought?
Bizarre.
It is bizarre. But it also shows you how natural log is the language of calculus, even to the point where Wolfram Alpha interprets it as natural log, even though I meant it to be common log.
Right.
What else do you have?
3 raised to the power raised to 2x plus 3 to the power of x plus 1 equals 4.
And we're adding those two things on the left, not multiplying them?
Yes, adding.
Thinking.
Would you take the natural log of all 3 terms?
Well, let's try that. I can take the natural log of the left side, and that's going to equal the natural log of the right side.
Oh, it's a bite. Okay.
That doesn't help.
No.
In other words, I can't do anything with that argument now. Why I was kind of hoping that it would be multiplication instead of addition, because then I could say
Natural log of 3 raised to the 2x.
yeah, hold on a minute. I'm wondering if I can take the natural log of both of these. See what happens if I do that. If I say the natural log of 3 to the 2x plus the natural log of 3 to the x plus 1 equals the natural log of 4, now I would not be able to combine those. I don't think I can do this step anyway. And if I could, doesn't help. Or does it? Let's see. If I move the 2x down in front, so I have 2x natural log of 3 plus x plus 1 natural log of 3 equals natural log of 4, at least I could solve that. In other words, it's now an algebraic equation that would allow me to solve it. But there's no way that the natural log of the left side is equal to the natural log of each of these separately.
Right.
I don't think. Hold on a second. Let's see. If I had 2 plus 2 equals 4, and I take the common log of that and the common log of that, is it equal to that? Well, that expression is 100 plus 100 is not equal to 10,000. So no, you cannot do that.
Okay.
I would have to take the log of the entire left side. I cannot take the log of individual pieces of it. So
Right.
if we go back to your problem, I know how to do that now. I got to do that. Yeah. I knew I had done it once before. So I knew I had to do it. Now let's see how we can solve this. This can't be that hard. This is kind of like some of the others you gave me. In fact, the very first problem you ever gave me, I was lucky that I figured out how to do it. I wasn't thinking about it.
Yeah.
I mean, I had to think about it to figure out how to do it. So what can we do here? 3 to the 2x plus 3 to the x plus 1. Even if I take the log of the whole left side, that leaves me nowhere. I don't know what to do with that. Are you allowed to use a calculator on these?
No.
Okay, so you can definitely not use a calculator to solve this, because again, if you could use a calculator, or if I could use Wolfram Alpha, I would put this as my y sub 1, this is my y sub 2, and wherever they cross is the solution for x.
Right.
If I cannot use a calculator, how the heck, what am I missing here? This was exactly how the problem was, right?
Yeah.
Well, what if I took one of those exponents to the other side? And now I take the natural log of both sides. Doesn't help. I'm going to be able to bring the 2x down to here, but I can't do anything with this x plus 1.
Right.
What else could I
Would bringing the 4 to the other side do anything?
Yeah, I was thinking that, right as you said it. I can't even turn that into a quadratic. In other words, if this was x instead of x plus 1, I might be able to work with it. Oh no, even that I wouldn't be able to do. Yes, I would. If that was this, that's a quadratic. In other words, if I let u equal 3 to the x, then what I have here is u squared plus u minus 4 equals 0. And then I could factor it and solve it. But the fact that it's x minus 1 in the numerator, or in the exponent,
Plus 1.
plus 1,
Now, if the negative 4 were a positive 3, could you take out the 3's and just have the 2x plus x plus 1 plus 1, or would that have to be multiplication?
you've just given me, I think, the solution. Put the 4 back on the other side. What we're going to do is we're going to use this as a base. In other words, if the top statement is true, then this statement is true. The log base 3 of that exponent is equal to the log base 3 of that exponent.
Okay.
That doesn't help me either. No. I think I'm along the right track, though. I don't know. I hate to spend more time on a problem that I can't seem to figure out how to do. And I don't think the solution is that simple. It's a weird problem. I'm not sure I've ever had a problem given to me quite like this, but it wouldn't be the first one you've given to me that was unique. I don't know. You got another one?
Yeah.
You only have 5 minutes. I hate to waste it on this problem that I don't know how to do. I'm going to draw a line under it, though, and after I hang up, I'm going to work on it a little bit and see if I can't figure out how to solve it.
All right. Pi to the power of 1 minus x equals e to the power of x.
Okay. Here we can take the natural log of both sides.
Right.
And the beauty of the natural log here is the right side becomes x.
Right.
The left side becomes 1 minus x times the natural log of pi, which is just a number. And now you just have to distribute. In other words, we now have an algebraic equation. Okay, so distribute that. So we got the natural log of pi minus natural log of pi x, or x natural log of pi is a better way to write that, equals x. Now move all my x terms to the right. So I have natural log of pi equals x plus x natural log of pi. Now factor out the x. And divide by that coefficient. So you end up with natural log of pi divided by 1 plus natural log of pi.
Okay.
That's what x is equal to. And that's simplified as much as you can do it.
Right. Okay. 0.3 Wait. Yeah, sorry. 0.3 times 4 to the power of 0.2x, all equal to 0.2.
Okay. Again, now we have an exponential expression. Can't solve it algebraically, but I can solve it if I can get logs involved.
Right.
Now, I can't take the log of both sides because I got this 0.3 over here. What I tried to isolate is that. Once I isolate that, then I can take the natural log of both sides. So the first step here is to divide both sides by 0.3. Okay, so now I have 4 to the 0.2x equals 2/3. Now, take the natural log of both sides. Allows me to bring the 0.2x to there, leaving natural log of 4 equals natural log of 2/3. And now I'm going to divide both sides by 0.2 natural log 4, leaving x all alone on the left. On the right, I got natural log of 2/3 divided by 0.2 natural log of 4. That's just a number.
Okay.
So the goal on all of these where you're given an exponential equation is to isolate the part that's the exponential part. Then you can take the logs, whatever log you like, but of both sides and turn it into an algebraic expression.
Okay.
This, incidentally, is a negative number. Whenever you take the logs of numbers between 0 and 1, you get negative numbers. When you take the logs of numbers greater than 1, you get positive numbers.
Okay.
All right, William, that's probably a good place to stop. I think I finally woke up from my nap that I accidentally took. I will talk to you next time.
Great. Thank you very much.
All right.
Have a good night.
You too. Bye-bye.